Okay, welcome back student to this section about infinite series of function. And let me just start reminding you what is an infinite series of function. We will start with a series of function f1, f2, f3 and so on. Okay, and this will give me another series. If you remember, we call it the partial or the sequence of partial sum, which is usually we call it S1, S2, S3 and so on, where Sn is the sum of the first n elements from the original sequence. Okay, and I will be interested in studying not the limit of the original sequence. I'm interested to study the limit of the sequence of partial sum, which I will denote it by the orange color, which is f. Now, what is f? F is the limit, if you want. F is just the limit of Sn as n goes to infinity, or it is just the sum from 1 to infinity for Fn. Which means if we try to sum all those functions, we will get a function which we call it f. And what we will do now is we want to study the properties of f by knowing the properties of f1, f2, f3, and so on. That's the whole idea. It is very much similar to what we did last time, but last time we were focusing here on the limit of the sequence itself. Now we are focusing on the sum of f. And that's exactly what we are. So let's do the first theorem, just to give us a heads up here. So theorem 1 in this section. And in this theorem, we will start with a sequence of function. And we will assume that the partial sum converges to f Now, what we will have, if each fn is continuous, then f itself is continuous. That might be a little bit confusing because we have seen something like this, but remember, I'm not talking about the limit of the sequence. I'm talking about the limit of the partial sum, which means the sum of all of them. So if you have a sequence of continuous function and you add them all, the result will be a continuous function. That's the whole idea. How we would prove it? The proof is as follows. Proof. We know, of course, I forgot to write something very important here. Converge uniformly. Remember, everything we have to do it is uniformly. So we know by assumption that Sn converges uniformly to f. That's the assumption. Okay. Now, each Sn is continuous. Why? Because it is a finite sum of continuous function. So each Sn is continuous. So what we have? We have Sn is continuous. We have uniform convergence, hence f itself is continuous. So the idea of this proof is what we did actually, we take the properties of f and we reflect them on Sn. And then we used what we know before, that if we have a sequence of Sn converges uniformly to f, the properties will be inherited as they are. So the idea here is what actually did, we took the properties here and we bring them back here. So now if this is continuous, this will be continuous. If this is bounded, this will be bounded. Integrable, integrable. Differentiable, with some condition, it will be differentiable. And that's what we will do next. Let's do the integration now. If those are integrable, this will be integrable, this will be integrable. That's the whole idea that we will do next. And this is theorem 2. Which is integration. So what's theorem number 2? Let Fn be a sequence of functions on AB, and the Sn converges uniformly to f, the same as before. Now if each Fn is Riemann integrable, on AB, then f is Riemann integrable. And this is the same proof we did for the continuous. And we have something extra. I will write it down, that if we take the limit of the sum, I can switch them. The integration and the summation can be switched if we have uniform convergence. Okay, so we have to prove two things. First, we have to prove f is Riemann integrable, and then we have to prove that the integration and the summation can be switched. Let's do the first part. Proof. I just want to remind you of my setup. F1, F2, F3, and so on. And then I have this S1, S2, S3, and so on. And this is converges uniformly to F. So the idea is I will take the properties of F and I will check, are they applicable to S? And if yes, they will be inherited to F as we saw before. So since Fn is Riemann integrable, Each one of them is Riemann integrable. How about Sn? Well, Sn is just the sum of f1, f2, and so on, which is the sum of Riemann integrable function. Now, if you remember, we have seen this before. If we're adding Riemann integrable function, the result is Riemann integrable. Hence, Sn is Riemann integrable. And because this Sn converges to f uniformly, we conclude that f itself is Riemann integrable. That's how we will do it. Okay, so we finished from the first part, and as I said, the idea is very clear. We take the properties of f and we check, are they applicable to S? If they are applicable to S, we can push them to f because of what we did before. Now, the remaining part is we need to do the integration, which is very much easy, is nothing. Okay, let's do the left hand side. So if we do the integration of the infinite sum, first of all, what is this? Now, if you remember, this one is very easy. This is just f. It is the limit of Sn. So let me write it down. This is just the limit of Sn. Now I know what is Sn. Sn is just f1 plus f2. So it will be the sum from I equal 1 to n. And now we know from what we did before, the limit and the integration, we will switch them, because the limit of the sum so we take the limit outside, and also we will switch the integration together. So it is the limit as n goes to infinity, or just let me write it down as summation of integral from AB. That's the whole idea of how the sequence will happen. Okay. Thus we finish from the integration. I think now you know what will happen is we will do the derivative. Number 3, theorem number 3 is the derivative. Again, the same setup, so I will not prove it. But remember, in differentiation, the idea is a little bit, there are some conditions we need to make sure they are there. If you remember, there are 3 conditions that we need to check. and from there we can continue. Okay, let's see for the differentiation. Now, if you remember, for the differentiation, we have to talk about the sequence of the derivative. So there are some layers here. We need to check them. If you remember, let me just take you back to those conditions. You have the sequence, and then you have three conditions. The derivative must be Riemann integrable. Okay. Fn dash will be converges uniformly. Of course, here I will continue with this one. And then there exists one point where the sequence is converges. Now there's a little bit of a difference because here we have to use the summation of Fn dash. So the differentiation will just go as before. So let f be a sequence of differentiable function and assume the three conditions. The third one is that the Sn converges at some point x0. The second condition, if you remember, was Sn dash converges uniformly. And the third condition is Sn dash is Riemann integrable. If we have those three conditions, then we can conclude that f itself is differentiable and what is f dash will be just the sum of Fn dash. The proof and everything will follow as before, so we don't need to go through it that much. Okay, now the last but not the least is the boundedness. What happened if every Fn is bounded? What can we conclude? And this will lead us to a very nice and useful theorem. Theorem number 4. It's called Weierstrass M-test. So just keep this word in your head. M-test is very important test. And what is this test? Now assume you have a sequence of function which is bounded. So every one of them is less than a specific number, mn, for some mn. So each one of them is bounded. Maybe they have different bound, but each one of them is bounded. Now, what can we say? If the series mn, remember this series of numbers if the series of numbers converges, then the series of function converges uniformly. So the idea of the M-test is that it will tell me if my sequence converges uniformly or not by finding a bound for each function and make sure that the series of this bound converges as numbers. Already we have seen this before, the series of numbers in the previous chapter. How we will show this? Of course, the idea is how I show that something is converges uniformly. We will use Cauchy criterion. Now, what is Cauchy criterion? We'll say let epsilon greater than 0 be given. And what would be the required from us is to find n if n is greater than n, then Sn of x or Sm of x minus Sn of x less than epsilon. So that's exactly what we want to prove. Okay, let's see how we will prove this one. Of course, we have number 1, 2, and 3. Let me start with number 3. Now, starting with number 3, Sm of x minus Sn of x. If we do it, this is f1 of x plus f2 of x plus fm of x minus f1 of x minus f2 of x until fn of x. This one minus this one. And now, if we do cancellation, the one that will survive is fxm m minus 1x and I think fn plus 1, because anything less than fn will get cancelled. Triangle inequality, each one of these is less than now each one of these already bounded by m, so this is m minus 1 and so on. Okay, now if you focus on this one, this is less than Tm minus Tn. You will tell me what is Tn, what is Tm. Tm is the partial sum of m. Now, what do we know about the series m1, m2, m3, and so on? It is converges, right? Let me write it down here for you just to make sure that we are following. Mn converges, so it is Cauchy. So there exists n, mn greater than n, then Tm minus Tn will be less than anything I want it to be. Of course, anything in epsilon. Epsilon over 2, epsilon over 5, but if things to happen must be less than epsilon, so I will choose it to be less than epsilon, and it will end the proof. So it is kind of just putting things together, and that's how it is. In the first part, now we finish from the proofs. Now what we will do next is we will go through some examples about what we did here.